Okay, and welcome back to another clip, and today we're going to be talking about atom economy. Now, to be perfectly honest, atom economy is one of the easiest things to work out, especially in an A-level, or rather AS-level exam, right? So, if you watched the last clip on percentage yield, you would have remembered that the percentage yield, it tells us the efficiency of converting reactants into products, right? It doesn't quite tell us how wasteful a reaction is. It tells us its efficiency of converting reactants into products, but it doesn't tell us exactly how wasteful the reaction is. You see, if we make, for example, if we make byproducts in addition to the desired product, which is what we want, the reaction is wasteful, right? Common sense, really. So, what is atom economy? Well, atom economy, folks, is really just the proportion, right? The proportion of the desired products compared with all the products. Not just one, but all the products formed. And the subtlety between atom economy and percentage yields can be a little tricky to grasp at times. So let's go on to talk about how we actually calculate atom economy. Okay, perhaps this is where the confusion lies with students. The formula looks the equation looks very similar to that of percentage yield. So atom economy, you work it out by getting the molecular mass of the desired product divided by the sum, right? So this sigma, the sum of the molecular masses of all the products, and it's displayed as a percentage. So we multiply by 100 in the last step. Let's consider two reactions. Oops. Let's consider a reaction A plus B going to form C, and let's consider another reaction A plus B going to form C plus D. Now, in both equation 1 and 2, right, the desired product is C. That is the desired product, not products. Now, you can clearly see that in reaction 1, we're forming only C, which is absolutely fantastic. We've got no byproducts, we've got no waste. In reaction number 2, we're also producing C, but we've also got D, which is a waste. It's a waste product. Unless we can actually find a use for it, it's a waste. So it's not really good. We don't want waste for a number of reasons. A, we have to deal with the cost of managing this waste in an effective manner. And B, it's just time consuming. It's time consuming unless we've actually got a buyer for this byproduct. We have to deal with waste. We have to deal in terms of the cost of taking care of this waste. Landfill sites are filling up, so we really don't want to produce any more waste than we actually can, I suppose. So if you had a choice between reaction 1 and reaction 2, we'd take reaction 1, assuming the reaction conditions were easy enough and manageable. So it's quite simple. We only want C. D is a waste product. And atom economy, if we go back to the last slide, tells us the proportion of desired products compared with all the products formed. In reaction 1, C is the desired product, and it's the only product which is formed. That's fantastic. We've got an atom economy of 100% there. C and D, C again is the desired product, D is waste. Therefore, atom economy is not going to be 100 because we've got some manner of waste product. Okay, so let's go on with an example. And in this example, we've got one bromobutane being reacted with aqueous sodium hydroxide to form, butane, 1-ol, and sodium bromide. So let's work out what the desired product is. The desired product is obviously this. It's the alcohol, it's butane, 1-ol. We've got a substitution reaction here, where the aqueous hydroxide ions have substituted the bromide, or rather the bromine, in the halogenal alkane. So it's a simple substitution, for which you should be able to draw the mechanism if you're doing A-level. Okay, so let's talk about how would we work out atom economy. I'm just going to simplify it A to E, A dot E, atom economy. So you'll remember it's the mass, the molecular mass, right, of the desired product, which is this over here, and the molecular weight, or mass, right, I suppose, the molecular mass of the desired product in this instance here is 74. And we're then going to divide it by the sum of the masses of all the products, which includes both sodium bromide and butan 1-ol. So we're going to have 74 again, plus NABR. The molecular mass of NABR is 23 plus 79.9. So if we get that together, we should get 74 over 176.9 is equal to 0.418. Now, of course, we've not multiplied by 100, so let's multiply by 100. So if we do 0.41 to turn into a percentage, it's equal to 41.8%. So the atom economy in this reaction here is 41.8%, which is rubbish, right? This tells us that even assuming even we had a percentage yield of 100%, we would get more than half the mass of the reactants. More than half the total masses of the atoms used of the reactants would be wasted, which would mean that we're only getting 41.8% of the atoms used in the desired product, which isn't great. And that's assuming we could even manage this 100% percentage yield. So it's not great. That's all there is to it. That's all there is to atom economy. It tells us how wasteful a reaction is. Okay, let's move on to another example. Let's have a look. You should be able to recognize these as the two methods of making ethanol alcohol. In the first one, we've got the hydration, starting off with ethene and water. And of course, the conditions are going to be phosphoric acid, about 300 degrees C and about 60 atmospheres. And of course, on the right hand side, we've got the fermentation, so we need yeast, in the presence of which provides the enzyme zymase, and we've got an optimum temperature of 37 degrees C. So in terms of atom economy, which one is better? Well, let's just analyze the equations first. On the one on the left, in the hydration, right, we have got ethene reacting with water to form only one product. This one product is the desired product. So immediately we can see that all the atoms used in this reaction are used to make the product only. So clearly, just from looking at this equation, we can see this is going to have an atom economy of 100%, which is fantastic. Right? It's absolutely fantastic. It's what we want. However, let's have a look at the atom economy on the one on the right, on the one for the fermentation of ethanol, where we're forming both ethanol and carbon dioxide. Now, obviously, carbon dioxide is going to be a waste. Right? It's something that we do not want. So, how do we work out the atom economy for this example here? What I'm just going to do is just split it up. Right, again, it's the same format as we did for the earlier one, except there's something that we need to be aware of, and I'm going to just circle it here just so that we're aware of it. Sorry. And that's the stoichiometry. The 2 moles of ethanol and the 2 moles of carbon dioxide. It plays a part in working out the atom economy. So let's start off. Atom economy is going to equal to the molecular mass of the desired product being ethanol in this situation here. Now, ethanol has a molecular mass of 46. However, we have to bear in mind that we're forming 2 moles of this, so 46 times 2. And then we're going to divide it by the sum of all the products formed. So in this case, we're forming ethanol. Again, it's 2 moles. Plus, we're forming 2 moles of carbon dioxide. The MR of carbon dioxide is 44. And that should come to a grand total of 92 over 180. And if we were to stick that into a calculator, so let's get my trusty calculator here, 92 divided by 180, multiplied by 100, we get a percentage yield, sorry, I beg your pardon, an atom economy of 51.1%. So clearly, the atom economy, and it's quite obvious really, the atom economy in the hydration of ethene is 100% compared to the fermentation, in which the atom economy is only 51.1%. This point, by the way, this point in atom economy may well be asked in a question asking you to compare and contrast the two processes of making ethanol. And you could well say, as a for a mark or two, you could well say that the atom economy in the fermentation is a lot lower than it is in the hydration of ethene. So one simple thing that you guys need to remember, and you've probably already gotten this from how the clip's been going along. If we've got additional reactions, so 2 reactants coming together to form only one product, we're always, as in the case of this hydration, we're always going to have an atom economy of 100%. Because all the atoms are being used to form one product only. And therefore, if we had any other sort of reaction besides addition, so substitution, or let's say elimination, right? Of course, because we're going to form byproducts also, so the atom economy will always be less than 100%, simply because we're forming waste products. Right, I hope it helps. It was a hard topic. To be honest, you just need practice. Main key point is do not forget the stoichiometry, right, in working out with the atom economy, because it is really easy to forget it. And please do not get confused between the percentage yield and atom economy. Remember, percentage yield only tells us the efficiency of converting reactants into products, whereas atom economy, it tells us the proportion of the desired products compared to all the products formed. Okay, I hope that helped. Until next time.